Hello, here is a quick tutorial about the practical that we have done about using a spectrophotometer, and I will briefly go through the calculations that we should have done in the practical session. So in the first question here, we were supposed to calculate the amount of the paranitrophenol that was used to prepare 1 milliliter of a 0% weight per volume solution, and we have been given a 0.5% weight per volume stock solution, so we've got 0.5% weight per volume, and this actually means that we've got 0.5 gram in 100 milliliter of solution. And I can multiply that by a factor of 10 so that I will get 10 times 100 milliliter. So 10 times 100 milliliter. And I've got 10 times 0.5 gram. And that gives me the concentration in gram per liter. So I've got 5 gram per liter. I can also just simply divide this here by factor 100. And then I would get how much I needed for 1 milliliter. So that would be 0.5 gram divided by 100. That would be 0.005 gram, which also would be the same as 5 milligram. So I need 5 milligrams of the substance for 1 milliliter of solution. Now we need to estimate the absorbance of the stock solution. And in order to do that, we need to convert this concentration that we have here, the 5 gram per liter, we need to convert that into a molar concentration. So we need to convert that to mole per liter. And we have been given the molecular mass of paranitrophenol, and I just simply write it in such a way that the mole is on top of the fraction line. 1 mole is equivalent to 139 grams. Now the mole is in the right position here, but I need to get rid of the gram unit here, and I can do that by multiplying this with the concentration that we just calculated here, because then I will cancel out the grams. So 5 gram per liter. The grams cancel out, and I have left the unit mole per liter, and that is exactly what I want. So I can write this as 5 over 139 mole per liter. And I can put that in the calculator, and I would get a concentration of 3.6 times 10 to the power of -2 mole per liter molar. So that is the concentration of the substance of the paranitrophenol solution. And now we need to find out and estimate the absorbance of this solution, so we can apply the Beer-Lambert law, or the absorbance equals the concentration times the extinction coefficient times the path length, and the path length is usually 1 centimeter. In our case it indeed was 1 centimeter, so we just simply can put in the numbers that we just calculated for the concentration. So that's 3.6 times 10 to the power of -2 molar times the extinction coefficient, which we've been given here, So we've got 1.83 times 10 to the power of 4 per molar and centimeter, and multiplied it by 1 centimeter. So in terms of units, the centimeter cancels out, the molar cancels out, and we have a unitless number for our absorbance. And if we put that into a calculator, we will get something around 658 absorbance. Now this is of course far too high to measure, so therefore we need to do some dilution steps. So estimated absorbance, that was 658 or something like that, 658, 659, but definitely too high to deal with it. So what we then want to do is we want to prepare a 1 in 100 dilution, and we want to have a 3 milliliter working solution from that. So the total volume should be 3 milliliter, and we need to figure out how much of this stock solution, that is our stock solution, how much of that stock solution do we need to get a 1 in 100 dilution, and the total volume should be 3 milliliters. So that's the task, and that's very easy when we work with dilution factor, because we can say, okay, we want 3000 microliter, 3000 microliter, that's the same as 3 milliliter, times 1/100, that's our dilution factor. And that would be, we don't even need a calculator for that, that would be exactly 30 microliter. So we need 30 microliter of our stock solution, and put that together with the dilutant so that we get in the end 3000 milliliter. So the amount of the paranitrophenol solution here would be 30 microliter. And the dilutant that we want would be, so that if we add it to the amount of dilutant, we would get 3000. So we just simply calculate 3000 microliter minus 30 microliter, and we get 2970 microliter that we would need to add dilutant to this stock solution to make up these 3 milliliter. So we can now prepare this solution, and we get a 3 milliliter solution. We can calculate the molar concentration of this working solution, because we know that we had originally a 3.6 times 10 to the minus 2 molar solution that we used, and we did a 1 in 100 dilution, so times 1 in 100, and that's quite easy to calculate. And again, we don't need a calculator for that, so that would be just simply 3.6 times 10 to the minus 4 molar solution, and that would be the answer here. So the molar concentration of this 1 in 100 dilution is 3.6 times 10 to the minus 4 molar solution. And we can also estimate the absorbance of this solution, because we know that our original solution, we estimated it to be a value of 658. And all we need to do is, again, we do a 1 in 100 dilution of that. So that gives us 658 divided by 100. That gives us an absorbance, an estimated absorbance of 6.58. 6.58. Which of course is still far too high to do something with it. In this part of the experiment, I wanted to demonstrate that it's really easy to figure out which way around a cuvette actually needs to be placed into a spectrophotometer. So I said that the cuvette has basically two different sides in a way. One is the stripy side where you can touch it, and the other side, 90 degrees to that, would be a clear side, and that actually should be the side that the light would go through. So if we place the cuvette with the clear side, in this case with this clear side, into the spectrophotometer, we should really get a reading of 0.00. However, if we place the cuvette with the ripped side, where you can actually touch it, into the spectrophotometer, light will be absorbed and we get a reading probably around 0.1 to 0.3 or something like that. And that indicates basically that the light is absorbed by this ripped side because we've put the cuvette the wrong way round. So if you are not quite sure how the light goes into a spectrophotometer, just try out the two directions for the cuvette. Just take it out, measure what your absorbance is, and then take out the cuvette, turn it around 90 degrees, and if the absorbance is now higher than it was before, then it was basically, this is then the wrong way because the light is absorbed by this ripped side. Okay, now we are doing another experiment here where we take our 1 in 100 dilution that we had up here, and we place, so we have our 1 in 100 dilution. So our working solution 1 in 100, and of this solution we take 100 microliter and add it to 2900 microliter of the diluent in the cuvette. So what we can do is we calculate now what the dilution factor would be. And that's quite easy. We can calculate the dilution factor because what we have done is we have taken 100 microliter of our working solution and we diluted these 100 microliter in a total volume of 3000 microliter. That's the 100 microliter plus the 2900 microliter. So this would be a dilution of 1 in 30. Now, when we measured the absorbance of this dilution in the cuvette, we probably got a value of around 0.22 or something like that. Now we want to figure out, is that actually what it should be? So we can calculate what we would estimate for this working solution that we just have in this cuvette. And again, that is quite easy because we said that our original working solution that we prepared, we said that this has an absorbance of 6.58 that we've prepared here in this step. So we would have this working solution has an absorbance of 6.58. And if we make a 1 in 30 dilution, we would dilute this absorbance, and that would also give us roughly an absorbance of 6.58 over 30, and that should give us something around 0.2 So these two values, actually, this one here is the estimated value, and it should be in line with the measured absorbance that you ideally should have. Here I ask you to do a little experiment where you just simply have your cuvette with the 2900 microliter in it, and you add the 100 microliter working solution to the bottom of this cuvette, and then observe what is happening. And I asked you not to mix. So what you should actually see is that the readings jump all over the place. So it would be probably like that, and so on and so forth. So the readings are all over the place and are not stable. So you don't get any stable readings, at least not in the time frame that we are looking at. So what is the reason for that? The reason is simple, because we didn't mix. We will see some kind of diffusion happening here. So here is a lot of diffusion, and we are basically measuring just simply diffusion, but not a homogeneous mixture of our substance. And that, of course, is very problematic, because we are just basically measuring random numbers. And why did I ask you to do this experiment? Because sometimes we do observe that we don't have a stable reading, especially when the mixing is a little bit tricky. So if you ever encounter an unstable reading, the most likely culprit for that is inadequate mixing. So if there is unstable reading, make sure that you have mixed the content of your cuvette properly. Okay, so what we would have done in this particular experiment, again, we would have measured our test cuvette, and that should give us an absorbance, as we said, at 405 nanometer. This should be around 0.22. What would happen if we change the wavelength at which we measure? So you've been asked to do a few measurements here of different wavelengths, and what you should have seen ideally, if we plot here the absorbance versus the various wavelengths here, and I abbreviate wavelength with the Greek letter lambda for that. So here we might have 380, 390, 400, 410 here, 410 and 420 nanometer. And what we should have seen is that we get something like that. So the absorbance goes up from 380, reaches almost a sort of a plateau, and then goes down. And that is just simply because in the lecture I told you we need the wavelengths, we need the energy of the light needs to be right in order to get the electrons into the correct into the correct position in the orbitals. And the light at 380 nanometer is probably not in the best position. Likewise, 420 nanometers, the energy is not right. So we would really need the right energy, which is provided by the light in this range here. Now, in this step here, we want to calculate the concentration and the number of moles in the test cuvette. So we did have 3 milliliter in the test cuvette. And so we had 3.6 times 10 to the minus 4 molar of our working solution. And we did a 1 in 30 dilution of that. So that's very easy to calculate. If we just put that into the calculator, we will get a concentration of roughly 12 micromolar. Or we can write this also as 12 times 10 to the minus 6 molar. So that would be our concentration of the paranitrophenol in this test cuvette here. So that would be 12 micromolar. And we can easily calculate the number of moles in the test cuvette. So we are looking for the unit mole, and we have 12 times 10 to the minus 6 mole per liter. That's the M here. That's our concentration. The mole is in the right place, but we need to get rid of the liter. So we need to multiply it by the volume of the test cuvette, and that is 3 times 10 to the minus 3. That's the milliliter here. And we need to make sure that we are in the right system here with liters and moles and so on and so forth. So the liter cancel out, and we have got 12 times 10 to the minus 6 times 3 times 10 to the minus 3. So that would give us 36 times 10 to the minus 9 mole, which of course we can also write as 36 nanomole for this step. Okay, so this is these calculations here. So what we need to do in this step here is we are using our working solution, and we said we've got the stock solution, this solution that we are using here. We use that as a stock solution, and we said this was, let's write down, we used this as the stock, and this had a concentration of 3.6 times 10 to the minus 4 mole per liter, so molar. And we want to make a working solution which contains 5 milliliter of this 20 micromolar solution. And we want to figure out how much of this stock solution we actually need to transfer. Now in the lecture I've given you this equation, C1V1 equals C2V2, which basically means the amount of number of moles that we take out of the stock must be the same as the number of moles that we want in the working solution. So all we need to do is take this equation here and solve for the volume of the stock solution. So that is C2V2 divided by our C1 of the stock solution, and we have here 5 milliliter times 20 micromolar, and write this as 20 times 10 to the minus 6 molar, divided by the concentration of this solution that we have, that is 3.6 times 10 to the minus 4 molar. The molar cancels out. We have the unit milliliter left, and when we put this into a calculator, we would get 0.27 rounded 8 milliliter, or in fact, which is the same as 278 microliter. And the amount of dilutant that we have here would be just simply 5 milliliters, so 5,000 minus 278 microliter. And that gives us, if my calculation is correct, we would need 4,722 microliter for this dilutant. So we prepare that, and now we can estimate also the absorbance of this solution. So again, we can say absorbance equals the concentration times the extinction factor times 1 centimeter. And the extinction factor we had for the concentration, that is what we have in this cuvette. So that would be 20 times 10 to the minus 6 molar times 1.83 times 10 to the power of 4 per molar and centimeter times 1 centimeter, and that cancels out. The molar cancels out, and we would get for this value, we would get for that an absorbance, an estimated absorbance of 0.366. So hopefully that is something that you found, that we get this. And that is actually should tally with what we measure, 0.366, at least somewhere near it. Now in this step here, we want to add then hydrochloric acid, 20 microliter of a 1 molar hydrochloric acid to our solution that we have in the cuvette, to the paranitrophenol in the cuvette. And what you probably will see, or what you should see, is that the absorbance really goes down quite dramatically, from 0.366 to almost 0. And why is that? Well, what we can do is we can draw the structure of the paranitrophenol. So we've got an OH group here, we have got the aromatic ring, and then we've got the nitro group, which looks a little bit like that in our structure here. We've got O, that is negatively charged, and the nitrogen is positively charged. So that is nitrophenol, paranitrophenol. And that is what it looks like. Now in alkaline solution, if we have an alkaline solution, we lose the proton that we have here in this position, and we would get something like this. So O, that is now negatively charged. We have the aromatic ring here, and we've got the nitro group here. So that's negatively charged, and that is positively charged. And this molecule here that you see is actually, we can do a little bit of isomerization. So what will happen to this electron pair? We can move the electron pair here. We can move this one down here. We move this one here. We move this one over here. So a lot of curly arrows, but what it boils down to is a structure like this. I probably should draw it nicely here and make an effort to get this correct. So we have the aromatic ring, which actually loses its aromaticity. So we've got an O here. We've got two electron pairs like that. And we now have the nitro group, negatively charged, and this one here is also negatively charged. And the nitrogen is positively charged. So what we see here is that we've got a double bond here. We've got what is called a quinone structure here. And we've got a double bond here as well. And this molecule, this type, actually absorbs the light at 405 nanometer. And it has to be this structure here. Now, on the other hand, if we add a proton to this molecule, then we convert this structure back into the acid-locked version here with the proton, and this one just simply does not absorb. Because we need these double bonds here, here, and here for the absorbance. We cannot form these double bonds here, and therefore this molecule just simply does not absorb the light. And that is actually what you should see, and how you explain that the absorbance goes down dramatically with this when we add acid. So I hope this makes sense, and you understand better the calculations that were required for this practical. Thank you very much for watching, and enjoy the rest of the practicals.